Electric vehicles dominated the automotive market in the early 1900s. They were ultimately defeated by internal combustion engines, not because of the motors, but due to strict limitations in energy storage, specifically the cost, low capacity, and heavy physical weight of early batteries. The modern automotive industry is currently racing to reverse that historical defeat. The objective is to achieve true performance parity with internal combustion engines by the year 2030. This table outlines the European Council for Automotive R&D targets. By 2030, a cell must deliver a specific energy of 450 watt-hours per kilogram for driving range and a specific power of 1,000 watts per kilogram for acceleration. This chart is a Ragone plot, plotting specific power against specific energy. The broad red oval represents current lithium-ion limits, while the star in the upper right quadrant marks the 2030 target. There is a massive operational gap between what current lithium-ion chemistries can output and the energy density required to match gasoline. Closing this gap is not a matter of simply building bigger battery packs. Reaching that star requires engineers to solve a set of inescapable electrochemical bottlenecks down at the atomic level, while simultaneously reducing the dead weight of the battery's structural housing. The energy inside a lithium-ion battery is stored through a process called intercalation. Lithium ions physically shuttle back and forth through an electrolyte, embedding themselves between the microscopic crystal layers of the electrode materials. Because this relies on physical ions occupying physical space, the absolute maximum energy a battery can hold is strictly dictated by the mass of the active electrode materials inside the cell. This bar chart shows the weight distribution of a lithium-ion cell. The cathode and anode active materials account for 58% of the total weight. The remaining 42% comes from the housing, electrolyte, and current collectors, components that store exactly zero energy. Furthermore, operating cells never reach their theoretical capacity limits. During the very first charge, the electrolyte reacts with the electrodes to form a passivation layer called the solid electrolyte interface. This irreversible chemical reaction permanently consumes a portion of the active lithium ions. This creates a paradoxical loop for vehicle design. If you attempt to increase the driving range by adding more active battery mass, you also add inactive structural mass. The vehicle gets heavier, requiring more mechanical power to move, which actively cancels out the added capacity. Static energy capacity only defines how far a vehicle can travel at a steady, slow pace. Real-world driving requires sudden surges of high power output, such as accelerating to pass a truck on the highway. The speed at which you can extract energy from the battery is strictly limited by the internal resistance of the materials themselves. This graph is a polarization curve. It is the primary diagnostic map for a cell's kinetic limitations, illustrating exactly how the battery's operating voltage drops below its theoretical open circuit voltage the moment a load is applied. The first barrier is shown in yellow. These activation losses represent the initial energy penalty required just to start the electrochemical reaction, forcing the lithium ions over the energy barrier at the electrode-electrolyte interface. The middle orange section illustrates ohmic losses. As current begins to flow, the inherent electrical resistance of the physical components, the electrolyte, the current collectors, and the electrodes, causes a steady, linear drop in voltage. Finally, under extreme power demands, we hit the severe gray drop-off on the right. These are mass transfer losses. This cliff represents a hard kinetic limit. The external circuit is demanding electrons faster than the physical lithium ions can diffuse through the liquid electrolyte. Because of these polarization losses, a high power demand forces the cell's voltage to plummet, leaving a significant portion of the stored energy trapped and unusable. Energy density and power density operate in direct opposition. Engineers measure the speed of this energy extraction using C rates at the top blue line. At a slow, optimal discharge rate of 0.2 C, the voltage remains high and relatively flat. But when the energy is pulled out 10 times faster at a 2 C rate, internal resistance sharply drags the voltage down, terminating the discharge cycle early. This adjacent chart proves that environmental temperature acts as a severe multiplier on these kinetic barriers. When ambient temperatures drop to 0 degrees Celsius and further down to -20, the liquid electrolyte thickens. Activation energy requirements spike, mass transfer resistance climbs, and the total voltage output collapses almost immediately. A battery's theoretical capacity is highly volatile in practice. Aggressive acceleration and sub-zero weather actively choke the atomic efficiency of the cell, severely cutting into the vehicle's actual driving range. The laws governing atomic diffusion and internal resistance are incredibly rigid. To compensate, the automotive industry is bypassing the chemistry entirely by radially re-engineering the structural weight of the vehicle. This diagram illustrates traditional pack engineering. Hundreds of individual cells are wired together in parallel and series to form secure, isolated modules. Those modules are then loaded into a heavy, reinforced outer pack. While this approach isolates failures and keeps the cells physically safe, it introduces massive structural redundancy. The steel and aluminum casings destroy the vehicle's overall energy-to-weight ratio. To reclaim that lost density, manufacturers are adopting cell-to-pack integration. By eliminating the intermediate modules entirely, engineers can pack significantly more active electrochemical material into the exact same physical volume. The absolute endpoint of this philosophy is cell-to-chassis architecture. Under this model, the protective battery casings literally become load-bearing structural members of the car. The cell wall and the vehicle frame are the same component. This density creates steep engineering trade-offs. Removing the empty space between modules eliminates the primary pathways for heat dissipation, making thermal management exceptionally difficult during high-power fast charging. Furthermore, because the individual cells are permanently bonded directly to the chassis, targeted localized repairs and end-of-life recycling become nearly impossible. These architectural extremes are necessary. They artificially boost the total energy density of the vehicle platform to compensate for rigid chemical limitations inside the cells. Reaching the engineering targets set for 2030 requires both the microscale chemistry and the macroscale architecture to operate in tandem. This Ragone plot visualizes exactly how that gap will be closed. Minimizing internal resistance with highly porous electrodes pushes capability outward along the horizontal power axis. Simultaneously, eliminating redundancy through cell-to-chassis integration pushes capacity upward along the vertical energy axis. Automotive engineers must optimize across two entirely different domains of physics at the exact same time, accelerating lithium diffusion at the atomic scale while physically deleting the steel frame of the car outside of it. Threading this needle is the mathematical pathway required to render the internal combustion engine permanently obsolete.